Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntech Consultants in California and the coordinator of the webinar series on behalf of CERDP and ESTCP. This webinar will consist of a brief overview of both programs, followed by two technical presentations. First, we're going to feature Dr. Linda Abriola from Tufts University, who will discuss experimental, mathematical modeling, and decision tools to better understand the processes controlling PFAS fate and transport in the subsurface. Linda's presentation will be followed by a Q&A session, and then we'll move on to Dr. Tim Strathman from the Colorado School of Mines, who will talk about his research efforts to develop a novel technology to treat PFAS in water and other high moisture content waste. Tim's presentation will also be followed by a Q&A session, and we will conclude the webinar with a longer Q&A session with both of today's speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and also provided to you in your webinar registration confirmation email. If you are unable to download Zoom, you can view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you are unable to view the slides, or if your screen freezes, try keying in Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, make sure to click the arrow next to the Join Audio button, select a speaker and microphone, and follow the prompts as they appear on your screen. If you continue to experience technical difficulties, call into the conference line shown here. You may also submit a comment using the chat box. Please remember to use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. In case of continued difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Keep in mind that we will also be live streaming the webinar on the CERDP and ESTCP YouTube channel at the link shown here. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. We do encourage you to submit them well in advance of the Q&A sessions. And when you do submit your questions, please add your organization name at the end so that we can identify it during the Q&A session. And just a quick reminder, the chat box should be reserved for technical difficulties, and the Q&A box should be reserved for questions for the speakers. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of CERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with CERDP and ESTCP since 2001, and prior to this, she was a research leader at the Battelle Memorial Institute, where she conducted scientific research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater treatment. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Thank you, Rula, and thank you to everyone who is joining us today. I'm very excited for this webinar. And before we get started, what I'd like to do is just give you a little bit of an overview of who we are, CERDP and ESTCP, and talk a little bit about what we're doing in terms of PFAS before we get into the technical webinars. So for those of you who don't know us, we are two companion programs. First is the Strategic Environmental Research and Development Program, or as we call it, CERDP. This is a joint effort between the Department of Defense, the EPA, and the Department of Energy. And it is a science and technology program We have been around for since 1991. We definitely operate in partnership between these three agencies, and our goal is to develop our research from fundamental to more applied research so that we create the knowledge and the technologies to impact real-world environmental management. CERTIP is operated in companionship with ESTCP, which is the Environmental Security Technology Certification Program. But this is a demonstration validation program operated out of the Department of Defense, and it is designed to take the knowledge and the technologies that are developed under CERTIP or other research programs and demonstrate them in the field. The goal being ultimately is this technology transfer of that information so that we can accelerate the commercialization or broader adoption of these different technologies. Our research is guided by a few environmental drivers. Number one is sustaining our testing and training ranges, facilities, and operations. And you can imagine this is very broad. It covers maritime sustainability, it covers the forward operating bases, it covers noise issues, just a tremendous amount of different environmental drivers in that realm itself. And then we also are looking to reduce the current and future liability. That also is quite broad. It can take the form of addressing pollution prevention issues, where we're looking at eliminating hazardous materials or processes at our military installations. And then we're dealing with issues from past practices where we've had impacted groundwater, soil, sediments, and some of these emerging chemical issues. And that's what we're dealing with here today, is addressing PFAS. So I'd like to point you in the direction of this resource. The web link for it is at the top of the page, and it will pop up here in the chat room in a minute. But what this graphic will take you through is all of the work that we are funding related to PFAS. And this is an interactive graph online where you can click any one of these boxes and it will take you to more information that has about what's been funded under that topic. It shows you from when we started in 2011 up until the present day. And every box on the upper graph represents CERTIP research topics. And so those all generally represent several projects. On the bottom half of the graph are our ESTCP demonstration projects. So I really encourage you, if you're interested, to go to this website and click around on there. You can get more information about what we're funding. Every project we fund has a project webpage that at a minimum describes the project, and then as we get further into the project, public documents are posted there for your information. It's very important to us to transfer the information that we're developing under CERTIP and ESTCP. We do this through a number of ways, from online videos, guidances, manuals. We have an EnviroWiki. We do in-person training when that is a possibility. And then ultimately we have our webinars where, you know, we're always trying to get this information out to people who would be interested and can use the information. Our webinar series happens roughly twice a month, and this is showing you some of the upcoming topics. All of this is online, and you can register for all of these seminars online at the link shown here. And you'll see a brief description for each of these webinars as well in terms of the topics we plan to cover. And finally, I would also like to mention our upcoming symposium. It will be December 1 through 3 this year. It actually will be virtual now. We just made that decision. This is an excellent opportunity to see something about everything we're funding in all of the different research areas. And I hope you would consider participating in that symposium. I think you have a lot of high quality research projects and demonstration projects to view. At this time, Rula, I'll turn it back to you to introduce our speakers.
Thank you, Andrea. I'm going to start with our first speaker, Dr. Linda Abriola, who is a university professor at Tufts, as well as the director of the Tufts Institute of the Environment. Linda served as the Dean of Tufts University School of Engineering between 2003 and 2015. She is a national and international expert on the multi-phase transport, fate, and recovery of contaminants in the subsurface. Linda is a member of the National Academy of Engineering, one of the highest honors in our industry, as well as a fellow of the American Academy of Arts and Sciences and the American Geophysical Union. She has been the recipient of numerous awards, including the National Groundwater Association's Distinguished Darcy Lectureship and the CERTA Project of the Year Award, twice. She received a bachelor's degree from Drexel University and master's and doctoral degrees from Princeton University, all in civil engineering. Linda, it's a pleasure to have you. Please proceed.
Hi, Rula. Thank you so much for that lovely introduction. Hi, everybody. I'm delighted to be here to talk a little bit about our recent progress on one of our CERTA grants. I'm going to talk today I'm going to give a little project overview and talk today about work that we've been doing on looking at interfacial accumulation and sorption of PFOS compounds and some of the implications for transport and retention, as well as some preliminary microcosm results and some key findings. Our research project is an integrated experimental and modeling study. And ultimately, our goal is to improve understanding of processes governing PFAS transport and persistence in complex AFFF source areas. And we want to use this understanding to develop and validate mathematical models and decision tools that will help capture these key processes and provide help in looking at the field deployment of new technologies. I'm going to start by talking a little bit about our studies on interfacial accumulation. We know that PFAS are typically co-released with organic chemicals, as well as they move through the unsaturated zone. So they're caught in the unsaturated zone profile. So we want to look at how these compounds behave at interfaces, whether they be organic water interfaces or air-water interfaces. So we're studying NAPL-water interfaces such as dodecane water, trichloroethylene water, and JP4 water, and we're looking at various PFOS compounds. We're using two methods to look at these interfacial tensions. One is a Wilhelmy plate tensiometer, and the other is the pendant drop method. So I'll begin by giving you some examples of measurements of air-water interfacial tension or surface tension. What you see here are plots that show surface tension as a function of concentration of PFAS. Here we have PFOA results and PFOS results. And we've measured these surface tensions in the presence of low dissolved solids and high level dissolved solids and midway in between. And the dissolved solids that we use here are representative of what is commonly found in aquifers in the US. And what you notice from these plots is that as the concentration of the PFAS compounds increases, surface tension decreases, and rather dramatically above a certain level of concentration. The other thing to notice here is that at different total dissolved solids concentrations, we have different behaviors with more retention and increasing surface tension reduction with increasing salt concentration. The other thing to notice from these plots is that different PFAS have different behavior, and you see a stronger total dissolved solids dependence of PFOS compared to PFOA. Now we can take these surface tension measurements, and because we know that interfacial tension is a measure of the surface concentration, we can estimate the surface accumulation of these compounds at the air-water interface. So what you see here are the plots that I showed you in the previous slide of PFAS as a function of concentration. And we can take these measurements, we can fit a nonlinear functional form known as the Zyskowski equation. And from that, we can use Gibbs equation to predict the surface excess, or the amount that is associated or accumulated on the air-water interface. And the bottom figure here shows you that estimation. And you can see that as you increase the dissolved solids concentrations, you have more surface accumulation of the PFOS compound. So this process of more interfacial accumulation is known as salting out, which suggests that PFOA and PFOS behave as though they were anionic surfactants. Now, if we look at a mixture of PFOS compounds, we've looked at a couple of AFFF formulations, 3M and Ansel. And you can see the air-water interfacial tension here on the left plot as a function of AFFF concentration. And we know that PFOS is the predominant PFOS in AFFF, and the concentration, the associated concentration of PFOS is shown as well on the bottom here. And what we see is that we can get tremendous interfacial retention reductions, particularly at very high AFFF concentrations. And those concentrations, like 3% AFFF, are consistent with what would be applied in a fire training site. We also notice that we get substantially lower interfacial tensions at high concentrations of AFFF compared to PFOS, and that's because PFOS has a limit to how much it can attach to the interface. And what we see here then is AFFF has other surfactant-like compounds that are contributing to its interfacial properties. And one of those compounds is sodium dodecyl sulfate. So we can take, so that's what I wanted to say about interfacial tension with air. And I want to now look at NAPL-Water interfacial tension and evaluation. And here I'm going to give you an example with dodecane. You see, this plot shows dodecane water interfacial tension as a function of PFOS concentration. And again, we see this salting out effect. And we see a reduction in interfacial tension with concentration. But at concentrations that might be typical of the field, we don't see substantial IFT reduction. So that we don't expect to see mobilization of NAPL due to this interfacial reduction at most sites. And the other thing to note is that this interfacial retention reduction suggests that PFOS is going to the dodecane water interface, and that suggests that these are oleophilic compounds. So now we use the same approach, and we can take the interfacial tension that we measured for different NAPL water interfaces. This is air, this is dodecane and PCE, and this is JP4. And we can estimate the surface accumulation or surface excess for, in this case, I'm showing you PFOA. And what you see is at low concentrations, for the air-water interface, we see much more surface excess. But as the concentration of PFOA increases, we start to see dodecane and PCE also having large amounts of accumulation of PFOA at the interface. So in general, these compounds we've observed prefer to go to the air-water phase over the NAPL water interface, but at higher concentrations, we can see substantial accumulation. And the accumulation at the NAPL interface could form a long-term source of PFOS if a NAPL was present in the source zone. So we can take those measurements, and we can also look at the NAPL water interfacial tension due to AFFF. And what you see here is a 3M AFFF and 3 different interfaces, dodecane water, PCE water, and JP4 water. And again, we see at larger AFFF concentrations, substantial reduction in interfacial tension. And at concentrations, again, typical of field applications, we see remarkable reduction, less than 4 micrometer, sorry. I'm sorry, I forgot the units here. Anyway, we see a large interfacial tension reduction, and this indicates that there's a high potential for mobilization of NAPL in regions where AFFF was applied. Now I want to turn to sorption data. And here we've been looking at different field soils. I have shown here PFOS sorption to 3 different field soils, washed Ottawa sand, Marden soil, and Appling soil. Marden soil and Appling soil are somewhat finer than the Ottawa sand, and they have higher organic carbon contents. What you notice here is that there's substantially more sorption in the higher organic carbon content soils. But the other thing to notice here is that the sorption is nonlinear, and it's well characterized by a Freundlich isotherm. So what does this all mean? What are the implications for these different partitioning relations? So what I've put together here is an example of the relative abundance in different phases or interfaces. On the left-hand side, we have washed Ottawa sand, and what you see here is how it would be distributed within an unsaturated profile. The blue indicates what is bound to the air-water interface. The gray, what is sorbed, and the orange is what is in the aqueous phase. And what you see here that immediately jumps out at you is that the aqueous phase mass does not predominate at all. And if you go to a finer grain material, what you see here is that much of the mass, almost all of it, is at the air-water interface. This is at the same saturation now, and what you see here is pure water and increasing amounts of total dissolved solids. So as total dissolved solids increase, you see more of that salting out effect and more captured at the air-water interface. But the take-home message here is that the air-water interface can capture a lot of mass in the unsaturated zone. Now, if we add a NAPL to this mix, we see the NAPL here in lighter orange. What you see here is that we have about as much partitioning going on to the NAPL water interface as is in the water phase itself. The other thing, so what I want to show here is this is increasing water saturation. As saturation increases, the area of interface between water and air decreases. And you see there's a reduction in the mass that's attached to the interface, and relatively more is sorbed then. Again, these are relative proportions. Here we hold the saturation fixed and increase the concentration of PFOS. And what you see here is as we increase concentration, we get more attachment to the air-water interface up to a point, and then you reach a limit because we saw that those curves for interfacial accumulation approach a limit. They have a Langmuir-like shape, and because they have this Langmuir-like shape, they have a maximum surface excess. Once that surface excess is reached, we see a decrease, relative percentage decrease of mass as the concentration increases. So you have this parabolic shape here. So we can take all of these measurements and we can combine them and the expressions that we develop from them into a state-of-the-art flow and transport simulator. And we have put these relationships into Hydrus. And I want to just show you some example simulations to give you a sense of how it behaves in the soil profile in terms of transport. And what you see here is a breakthrough curve. So we have normalized concentration, and we have pore volumes, which is a surrogate for time, okay? And the dotted line is a conservative tracer that has no sorption and no attachment to the air-water interfaces. And what I'm showing here is a system that only has accumulation on the air interfaces. And what I'm showing is the effect of total dissolved solids on the breakthrough curve. And as you increase from molecule water to medium and high dissolved solid concentrations, what you see is that you get a retardation in the breakthrough and you get much more tailing. On the right-hand side, I'm showing the effect of concentration. Recall again that this is a normalized concentration. So when you have a high PFOS concentration, relatively less mass is going to the interfaces. And as you decrease the concentration, you see much more retardation in the breakthrough because a greater portion is being retained on these air-water interfaces. And that's a consequence of the nonlinear shape of this retention curve. So we can also look at what happens when we add sorption to the mix. And here I have, again, the breakthrough curve for a conservative tracer. The blue line here is what happens just with soil sorption. Just with interfacial sorption, we have the green curve, and with both, we see the red curve. The left is for Ottawa sand, the right is for unwashed Ottawa sand. Unwashed Ottawa sand has a number of fines, which has a larger sorption capacity. And we see on the right-hand plot that, in fact, the sorption has more effect than the air-water accumulation at this saturation. And what you notice here is that the effects are additive, and the relative importance then of the mechanisms will differ with soil type. But in general, you're going to see more retention in higher organic carbon soils, and sorption will be more important in those higher organic carbon soils. We can also look at the profiles. And here I have two infiltration profiles, one associated with sorption only, and one associated with sorption and air-water accumulation. And what you see here is, remember, these are the aqueous phase profiles. So we have depth versus normalized concentration. So the pulse injection was 10 pore volumes. So after 10 pore volumes that we fill this whole capacity up 10 times, the front has made it halfway down the profile if we have just sorption. However, if we have sorption and air-water accumulation, the front has made it less than a third way down the profile. So you can see the importance of air-water accumulation again. And the red lines are 80 pore volumes. So that's a substantially large time of replenishment of the recharge. And you see that the PFOS here has penetrated not very far after 20 pore volumes, while with sorption only it's penetrated very far in the profile. So much of the mass retained on the air-water interfaces in the profile causes a reduction in the amount of mass in the aqueous phase and its slower propagation. So this is just another way of looking at those same simulations. And finally, I just want to give you some preliminary results from some microcosm experiments that have been being conducted under our project. We're working with AFFF impacted soils from sites at Air Force bases. The results I'm going to show you here come from Robins Air Force Base. So we're working with a native microbial community in a surface soil from Robins Air Force Base that was in an AFFF impacted area. And we're looking at the transformation of a PFOP precursor widely used in the manufacturing of fluorotelmer-based products. And that is an 8,2-fluorotelmer alcohol. And to our knowledge, this is the first study of the transformation of a fluorotelmer alcohol in an AFFF impacted soil. And what we have done is look at a series of batch microcosms with live treatment, where we have soil and medium, and we're using dichloroethene glycol butyl ether as an electron donor here. And we have abiotic control, live control, and medium-only control as well, so that we can definitively say that the transformation we see is due to the microbial community. And what we found here is that in the control, we have very little transformation of the fluorotelmer alcohol, but we see relatively rapid transformation in the microcosm with the live impacted soil. And the half-life is less than 5 days here. We also see polyfluorohydrocarbon metabolic transformation. These are the products that we've observed. And the terminal P product is PFOA. And so we see an increasing amount of PFOA with time. And at day 90, we had about 6% of the total mass was PFOA. And at this point, I believe that very less than 10% of the mass was remaining of the fluorotelomere alcohol. So none of these metabolic products was visible in the controls. So we think we have conclusively determined that this transformation is due to microbial transformation. So what does all this say so far? We've seen that PFOS compounds accumulated air-water and NAPL-water interfaces. These compounds are oleophilic and they have surfactant-like properties. Air-water surface accumulation is going to significantly retard PFOS transport in the unsaturated zone and lead to substantial mass retention in unsaturated soils. So very little of the mass is actually going to be in the water phase itself. PFAS sorption and interfacial accumulation are nonlinear functions of concentration, and this becomes very important when you're trying to predict fate and transfer, mass transfer. Total dissolved solids substantially influences the interfacial accumulation. We see this salting out effect at both air and NAPL-water interfaces, and there's greater accumulation at higher total dissolved solids. NAPL mobilization by PFOA and PFOS is not expected to be important at typical field concentrations. However, we see that AFFF formulations at higher concentrations could cause NAPL mobilization, and it would be expected at typical concentrations applied at the field. We think that these interfaces can serve as a long-term PFOS source in the saturated zone or unsaturated zone of NAPL is present in particular, and in the unsaturated zone, it's going to serve as a source at the air-water interface as well, and retarding migration. And we saw that one PFOA precursor, 8,2-fluorotelomere alcohol, was rapidly biotransformed to poly and perfluorinated metabolites in aerobic AFFF impacted surface soil, and the half-life was less than 5 days. So our project is, again, its goal is to increase understanding of key PFOS retention and retardation mechanisms that are going to control the elution from the source area and transport from the source area. This is to help improve site evaluation and risk assessment. We're developing a database of retention properties for representative PFOS in field soils. We're filling a key gap in knowledge regarding the biotransformation of precursors in AFFF impacted soils and aquifer materials. And we're developing modeling tools for prediction of the distribution and fate of PFOS in source zones, and for the potential for continuing releases and the likely success of natural enhanced attenuation. So I thank you for your attention, and I want to acknowledge my co-PIs, Kurt Pinnell, John Christ, Natalie Capiro, and Tom Phelan, as well as senior personnel, Masoud Arshadi and Jed Costanzo, and PhD students Chen Lu, Sheng Dong, and Fei Yan, and Anna Guedes. And these are some papers that have come out of our work recently, and I thank you for your attention.
Great, thank you so much, Linda. We've received a number of questions for you. We're going to start with one from the Naval Research Lab in DC. Have you looked at the micelle structures of PFAS in water and dodecane under various additive concentrations?
My colleague Kurt Pinnell is starting to look at the phase behavior of these compounds. And I know that there are other projects within CERTIP that are funded to look at this as well. What we have seen, I didn't show any results from FOSA, but what we have seen is micellar formation at higher concentrations of FOSA, and we haven't yet been started to sort out the behavior in AFFF formulations, but we are looking at the micelle formation in individual constituents and trying to get a handle on that. It's, as you know, it's very complex.
Great, thank you, Linda. A follow-up question also from the Naval Research Lab. Have you analyzed the elemental and compound characteristics of the sand used in your work?
Yeah, I believe that the sands that we have used, that information is available. These are sands and soils that we have used in other projects, at least the ones that we've been using for the sorption studies. For the Robbins Air Force Base material, we are in process of looking at the elemental composition there. I don't have the results currently. My colleague Natalie Capiro is working with her colleagues at Auburn to look at that.
Thank you, Linda. There's a question specific to the database and the data. Is that captured in the resource papers you have directed us to?
The data that I presented today, the interfacial tension data, is captured in the first publication. We have just submitted a publication that captures the information on the NAPL-Water Interfacial data, and that is currently under review for publication, and we hope to get that published as soon as possible.
Great, thank you, Linda. And here's a question from the state of Wisconsin. Do your modeling results suggest that air-water interface effects can be neglected in modeling transport if PFOS and PFOA are below a certain threshold concentration?
If your goal in modeling that is to look at the rate of transport, I would say that you cannot ignore the accumulation at the air-water interfaces. It is substantial. And it's a substantial amount of the mass at low concentrations, so it should not be ignored. If you're concerned with retention and rate of migration, it should not be neglected.
Great, and another question from Massachusetts Department of Environmental Protection. It is understandable that it is easier to show physical effects at higher concentrations. What can we expect for air-water interface at lower concentrations, for example, at the 10 ppt level?
So all of our measurements were conducted about the, at the sort of the 100 ppb level. So I guess what I would say is the focus of this work right now is looking at source areas where we expect the concentrations to be somewhat higher. I don't know if I can really talk about the PPT level. I wish my co-investigators were here to discuss that a little bit. But I think that the air-water interface partitioning, it's unlikely that you're going to see unsaturated zone is importance in areas. I think where you're seeing the PPT levels is most likely in the plume, where the air-water interface is not relevant, and there you only have to worry about absorption processes primarily. So what we're really focused on is the source area, and so that's why we're looking at somewhat larger concentrations. I can't really say too much about the PPT.
Thank you, Linda. This is a question from EPA. Does a DNAPL versus an LNAPL make a difference on AFFF water interface partitioning?
Well, from our results, you see that that the air-water interface partitioning was actually, oh, you said air-water or NAPL-water? You're talking NAPL-water interface, yeah. The NAPL-water interface partitioning, we saw actually similar partitioning to dodecane, which would be similar to a fuel oil, and PCE, surprisingly. And but jet fuel, which was sort of half diesel, half gasoline, we saw that the partitioning was less there. So it appears as though the extent of partitioning is more related to it's an organic phase as opposed to its structure at this point. We have measurements of those three compounds, and we see the same extent of partitioning in a LNAPL and a DNAPL in those two examples.
Thank you, Linda. This is a question from the New Jersey Institute of Technology. For the microcosm study, how did you quantify the precursors and their products? And how about the mass balance for the 8,2 FTOH transformation?
Okay, good questions. The analyses were conducted actually at Brown University. So they were, the microcosm studies were done at Auburn and the samples were transported to Brown. They were conducted with LC-MS-MS, and we had targeted certain compounds based on previous publications on transformation of this fluorotelomere alcohol in different types of systems. And so we were looking for targeted compounds. What you observed is that we did not have good mass balance, and we obviously missing, I think, something like 60% of the mass. So right now we're pursuing some untargeted analyses to see whether we can account for, we believe that there are other metabolites present that we did not seek, and we are looking to see what they would be to try to map the pathway. But that work is in process.
Thank you, Linda. And here's a question from the Program Manager for Weapon Systems and Platforms at Certifin ESTCP, and it relates to the nature of PFAS. Can you go over your rationale for the oleophilic nature of PFAS, please?
Can you repeat that, Rula? I'm sorry. The rationale for the what?
The oleophilic nature of PFAS that you referred to in your presentation, Linda.
Yeah, well, just the rationale is that the compounds are moving to the oil-water interface, and they seem to prefer to be at the oil-water interface. So that's really all I can say at that. My colleague Kurt Pinnell could probably give you a much deeper answer. I'm sorry he's not here to discuss that, but I can ask him and try to get back to you at the end of the Q&A if you'd like.
Thank you, Linda. I'll forward you the information. All right, maybe moving on to a few broader questions before we go on to the next presentation. Can you elaborate on the next steps in your research, Linda? What's next?
Oh, sure. So you've seen that we've been looking at surface accumulation and sorption for single PFAS compounds. We want to try to we are creating some mixtures of compounds to look at potential competitive effects. We believe that some of these processes they're not really partitioning processes per se, particularly for the sorption. So we think that we will see some competitive effects when we go to that. We also are moving to column investigations. We've basically done some hypothetical simulations here. Now we'd like to try to validate that this is actually what happens in the column profiles. So we're going to be doing some column investigations. And we're going to proceed with some microcosm studies looking at iron reducing conditions with the fluorotelomere alcohol. So those are the next steps in our research.
Thank you. And Linda, this is one last question here, and it relates to the ability of commercial environmental labs to perform the necessary analyses to determine the site-specific partitioning of PFAS. Are you aware of any commercial labs that can do this, or are these capabilities limited to academic labs? Well,
what we're trying to do is develop tools that will allow us to estimate this sort of partitioning behavior for example, at air water and NAPL-Water interfaces. If we can measure these interfacial tensions, and we have soil moisture relationships for the particular media, we can estimate the interfacial area and we can estimate the interfacial accumulation. But this is not, these types of measurements are not being regularly conducted, to my knowledge. This is still research.
Thank you so much, Linda. We did receive 38 questions for this part of the presentation, so we're going to save some of these till the end, time dependent, but as a reminder, you can download Linda's slides from her webinar webpage and refer to them in the future. And Also, her contact information has been included, so by all means, feel free to reach out to her for additional questions. But we'll try and get to as many questions as we can towards the end. At this point, I'd like to thank Linda again and transition to our next speaker, who is Dr. Timothy Strathman. Tim is a professor in the Department of Civil and Environmental Engineering at the Colorado School of Mines. He also holds a collaborative research appointment at the National Renewable Energy Lab and is also a member of NSF's Reinventing the Nation's Urban Water Infrastructure Engineering Research Center. Tim's research focuses on the development of innovative technologies for the remediation of PFAS impacted media. He is also interested in the advancement of hydrothermal processes for valorizing waste streams by producing fuels, fertilizers, and other valuable products from these waste streams. He is the recipient of an NSF Career Award, and he currently serves as an associate editor for Environmental Science and Technology. Tim received a bachelor's and a master's degree from Purdue University and his doctoral degree in environmental engineering from the Johns Hopkins University. Tim, please proceed.
Thanks, Rula, for that nice introduction. Yeah, today I'm going to talk about some of the results of a recently completed limited scope CERTIP project where we were investigating the potential development of an innovative technology that could achieve complete destruction of PFAS, which we're referring to now as hydrothermal alkaline treatment, or HALT PFAS. So let's see here. Just what I'm going to talk about today is, first I just want to introduce the ideas behind what the needs are for, in particular, are for new destructive technologies for PFASs. And then I want to particularly introduce hydrothermal processes for those that aren't familiar with them, and then focus on the results that we obtained from this, this study where we demonstrated PFAS degradation and defluorination. And then I want to wrap it up with some outlook and opportunities. I also want to acknowledge my co-PIs on this project at this point. That's Chris Higgins here at Colorado School of Mines, as well as our moderator, Rula Deeb from Geosyntech. Okay, so when we look at the current situation for treatment of PFAS, we basically have a situation where we're largely focused on removal technologies, but not necessarily destructive. And some of these technologies, like granular activated carbon adsorption and ion exchange, are highly effective for treatment. But at the same time, while they can remove PFAS and achieve very low standards or meet these very stringent low PPT standards, they produce a residual byproduct stream that requires some further management, if we ultimately want to destroy the PFASs. And so, but the destruction of PFASs has proved to be extremely challenging. If you look to the literature, you see that there's very little success in terms of widespread across the board treatment. And this is largely due to the high strength of carbon-fluorine bonds, which are among the strongest bonds in organic chemicals. As a result, there's been, for example, really few claims of biodegradation. There's some recent reports of very slow biodegradation under highly specialized conditions, but it's unclear whether or not in situ soils can be and aquifers can be sort of set to the conditions for that. They're also unreactive with common drinking water chemicals that we use in facilities today. And it's likely that we're going to need more intensive interventions, energy in the form of thermal energy or production of highly energetic radicals. And as a result, you know, if you look in the lay press, like here in the Denver Post, these are now being referred to as these forever chemicals because of their tendency to persist indefinitely in the absence of some active interventions. So my group has been investigating hydrothermal technologies for several years now, but we were more focused on, as Rula mentions, transforming biomass like algae and wastewater sludge into renewable fuels by application of these. And for this project, we wanted to see if these same hydrothermal reaction conditions could affect PFAS fate or ideally mineralize the PFAS. So when we refer to hydrothermal processes, we're really referring to water that's maintained above its typical boiling point of 100 degrees, but below the critical point, which is about 375 degrees Celsius. So this is water that is greater than 100 degrees in a pressurized vessel. So it's maintained in that condensed liquid phase. And as we raise the temperature of water above the boiling point in these hydrothermal conditions, water takes on some unique properties. It becomes simultaneously more acidic and basic, and it becomes, from a dielectric constant standpoint, more like a polar organic solvent. So there's a lot of unique chemistry that goes on there, which is why the biofuel industry is exploiting this to break down complex organic solids like algae and reform them into liquid oils. And so in this project, we wanted to see if we could apply these same reactive conditions to affect PFAS transformation. And one thing I want to mention is that it's somewhat counterintuitive at first when you think about it, but it takes significantly less energy to heat water that's in a sealed vessel from, say, 25 degrees to 350 degrees Celsius than it simply does to just evaporate water. So if you have any destructive technology, thermal or otherwise, that requires first drying the material, so incineration or any other thing like that, you have to drive all the water off first, and that's much more energy intensive than heating to the conditions that we're talking about here today. Okay, so for this initial proof of concept limited scope project, we focused on bench scale batch reaction studies where we evaluated the transformation of PFAS. So I'm showing just here pictures of some of these little mini stainless steel tube reactors that we've focused on in our experiments, where we just added water together with the PFAS of interest or the PFAS mixture like AFFF, and then we added different amendments that I'll talk about, different potential reactive amendments, and then we heat this to the temperature of interest, typically in the range of 200 to 350 degrees Celsius, before quenching the reactions and opening them up. And then we analyze the resulting solutions by a variety of techniques. We track the degradation of the PFAS using high-resolution LC QTOF MS analysis, as well as LC tandem mass spec to track the PFASs. We also used fluoride ion selective electrodes to quantify release of inorganic fluoride ions. And then we did some experiments using nuclear magnetic resonance spectroscopy to really look bulk at the the fluorine speciation in how it's bonded. So we can tell the difference, for example, between fluorine that's bonded to an organic carbon atom and fluorine that's just present as fluoride ion in solution. Okay, so we started out in our very first experiments. We just wanted to screen a whole range of potential amendments to see if they would promote defluorination of PFOS. So what I'm showing here are the results of this survey where we measured in the bars here, the light blue bars, is the percent defluorination that we observed for a 50 milligram per liter PFOS solution, maintained for 90 minutes at 350 degrees Celsius in the presence of each of these different amendments that I'm listing here on the bottom of the x-axis. And this included a variety of acids, bases, salts, oxidants, reducing agents, and even some metal nanoparticles. And what we found from this, if you look at the results of the bar, is that, not surprising to us, that for many of the amendments, that there was very little effect, right? That we don't see any appreciable defluorination. But we did observe for a small number of amendments that we got significant defluorination. So in these initial tests, we saw, particularly for 3 of the reagents, potassium ferrate, sodium borohydride, and sodium hydroxide, we saw 80% or more defluorination in the samples. And so although you know, these 3 reagents, one includes an oxidant, the ferrate, one includes a reducing agent, the borohydride, and one is a base, sodium hydroxide, what we found is that from a series of different tests was that really all of the defluorination activity was related to the fact that these 3 reagents all tended to cause the pH of solution to go to very high values. So it was really related to their effect on solution pH. They're causing this alkaline conditions, not because of their oxidant or reductant behavior. So because of this, we then focused the remainder of the work I'm going to talk about on just sodium hydroxide, because this is a very low cost reagent and it's stable and easy to use compared to the other 2 reagents. So we also found that the extent of defluorination and also PFOS destruction is also influenced by the reaction temperature as well as the alkali concentration. For example, here I'm just showing in this plot the extent of PFOS removal and percent defluorination, which we just define as the amount of fluoride that we detect as just inorganic fluoride ion relative to all the fluorine that's in the initial PFOS molecules. And we see, as we might have expected, that as we increase temperature, we see increasing defluorination and destruction. Also here, these plots show that we saw that the kinetics of PFOS destruction are also linearly related to the concentration of strong alkali that we had to solution. So we see that as we increase alkali concentrations from 1 to 5 molar, we see a linear increase in the reaction rates. And I'll come back to that when we talk about our proposed mechanism there. In terms of looking for byproducts and tracking the intermediates and final reaction products, which is very important, what we tended to see was that we saw stoichiometric formation of fluoride ion with little in the way of detectable organic intermediates. And I'm showing that kind of over here on the left. I'm just showing the percent defluorination as a function of the percent PFOS degraded under one of our reaction conditions. And what we see is that although there is some lag in defluorination relative to destruction, if we track it long enough, we have a relatively good closed mass balance on that. In terms of the intermediates, we did see some, when we start with PFOS as a starting reactant, we do see very small concentrations of perfluoroalkyl carboxylates. But as you can see here on this upper right plot, it was a very small percentage of the initial PFOS. So I think at most we saw, you know, something like 2.5% of the initial PFOS was ever detected as an organic intermediate. And if we track this further, it goes to 0. And this is not surprising to us, because when we conduct experiments where we start with perfluoroalkyl carboxylates like PFOA, they degrade much faster and don't even require alkali addition. So I'm just showing here a plot of a reaction of PFOA at 200 degrees Celsius, so 150 degrees lower than the temperature used for PFOS, and with much, much lower alkali added in this experiment. And we see that it degrades rapidly. So moving on from those experiments with PFOS, we wanted to see, does this actually, this same process work for the wider range of PFASs that would be detected in AFFF mixtures? And what we found is sort of the short answer is we did see that every single PFAS that we detected in 2 different AFFF formulations was completely degraded to non-detectable levels in short order, and we observed full complete fluoride release based upon the estimated fluorine contents of these AFFF mixtures. So it appears that whatever mechanism occurs, it occurs broadly for all fluorinated chemicals that appear in AFFF mixtures. Based on these results, we proposed a tentative mechanism that involves an alkaline hydrolysis mechanism. That is a nucleophilic attack of the hydroxide that is formed under these conditions. And this leads to cleavage of the head group and ultimately to defluorination and mineralization of the resulting PFASs here through a series of different steps. And finally, as a proof of concept, we tested the use of this HALT technology on several contaminated groundwaters and soils collected from Department of Defense sites around the nation, including a soil that we collected from Wurtsmith Air Force Base here. And what I'm showing in Michigan, and what I'm showing here in this table is the detected concentrations of a series of PFASs in the soil before treatment. And just as a summary, what we observe after 90 minutes of treatment in under these hydrothermal conditions. And what we saw is that greater than 90% of every PFAS we detected in the soil was removed during that time, most of them over 99%. Some of the perfluoroalkyl sulfonates like PFOS and PFHXS, which are generally among the most recalcitrant of this PFAS class, less of them were degraded, but of course if we follow the reaction for longer time periods, we see that ultimately these go below detection levels as well. Now, one of the advantages that we see for application of this technology for dealing with concentrates is that, again, it should require significantly less input heat to drive than a process like incineration, simply because we avoid having to evaporate all the water in the sample. So if we're talking about aqueous or wet type samples, including wet soils, we would anticipate that this process requires much less energy. And here I'm just showing some very simple rough calculations of the heat requirements to heat a wet sample to the conditions of interest. And if we compare them between incineration and hydrothermal treatment, we can see that it's significantly less input energy. Now, I wouldn't propose that this technology would be used to directly treat dilute groundwater. It's still far too energy consuming for that kind of process. But where we see it being applied is any place where you would normally think about applying incineration or other kinds of thermal destructive technologies. Hydrothermal treatment could be used as an alternative. Some of the applications that we're thinking about as we go forward certainly are application for concentrate management. So things like ion exchange waste regenerant brines or membrane concentrate streams that would be generated during removal processes. Also destruction of AFFF stockpiles that are unused, that have maybe the legacy formulations that have been banned. Also industrial waste streams where we have higher concentrations and there's a need to ensure that we're mineralizing those streams. And then in separate work, we're also looking at wastewater biosolids and the application to simultaneously apply hydrothermal processes to generate valuable byproducts like biofuel and also achieve PFAS destruction. So just in conclusion from the results that we've obtained from this study is that we do think that we've introduced a promising new technology, and it's worth noting to us that other groups are now getting into the game and looking to apply this or similar technologies, and so this is definitely of interest to us. What we find is that hydrothermal conditions, together with just simple low-cost alkalis like sodium hydroxide, potassium hydroxide, or lime, can promote PFAS destruction and defluorination. And the full suite of PFASs that we detected in AFFF, which is many more than just the simple perfluoroalkyl acids, were observed to be fully degraded to non-detectable levels and defluorinated with reaction time. And we've also saw successful tests with actual PFAS contaminated soils and waters that have been collected from DoD sites. Some of the benefits to DoD, of course, is that we think the technology is well suited for dealing with wet PFAS-containing waste, which might include source zone sediments and soils that have significant moisture content. This could be also liquid investigation-derived wastes that are generated on sites or unused stockpiles. We believe it's a lower energy alternative to off-site incineration, and it could be amenable to on-site treatment technology development. And that's one of the directions we're going, is to think about how you could use this as a mobile on-site treatment unit. We have a few publications already related in this area that I'm listing the references here, and that describe some of the work I'm talking about today, and we're working on a couple of additional papers that detail the findings with respect to AFFF mixtures and also the contaminated soils and groundwater. And with that, I'd be happy to answer some questions.
Great, Tim. We have a bunch of questions. We're going to start with one from the Department of Environmental Quality in the state of Oregon. Is HALT likely to be practical for treating landfill leachate?
I want to apologize now just because there is a fire alarm going off in my building, but I think it's just testing some fire alarms. So the question was, how would it deal with landfill leachate? That's an actually interesting question. That's an area that we are looking into ourselves with some people, and we would believe that it would be. It's an aqueous waste stream, and so it's an interesting area that we haven't investigated, but we would like to definitely.
Great, thank you. A second question from the Naval Research Lab in DC. Is HALT able to completely degrade the CF bonds in terminal CF3 groups, especially such groups in branch PFAS components?
It's a good question. We believe it is. I think it's hard to track specifically just the terminal groups in order to know that for sure. I would say the evidence that we have for that would be that it would accomplish that would be just simply our fluoride mass balance is closed quite well. If we look at our nuclear magnetic resonance spectroscopy, which does give us a kind of an overall picture of the fluorine chemical speciation in the system, we see that all spectral features related to chlorofluorine bonds, including features that would be for terminal CF3 groups, are eliminated, and we are replaced with a single spectral feature consistent with fluoride ion. But I think this is a good, important question. One of the things this might lead to is the questions about formation of volatile fluoro species like fluoroform, which could be a concern because of either toxicity or their greenhouse gas properties. We did do some analysis of gas phase products, and we did not detect any volatile organofluorine species like fluoroform. Those were initial studies, so we need to confirm that, but we don't see any evidence that there's persistence of particular bonds like that. But one way to investigate that would be to look at some individual structures that have only terminal CF3 groups like trifluoroacetic acid or triflic acid, which is the sulfonate analog.
Great, thank you. This is a question from the North Carolina Department of Environmental Quality. In the process that you described, are you able to capture the fluorine element as a gas?
We don't capture it as it's a good question. We don't capture it as a gas because it ends up as inorganic fluoride ion in solution. If we needed to capture that and recover it, we could potentially use something like calcium to precipitate it if that was of interest.
Thank you, Tim. And here's a question from another state, Department of Ecology, State of Washington. Have you looked at the effectiveness of your treatment technology for AFFF concentrate?
Yes, in fact, the experiments that we looked at we did them with AFFF, were done at a variety of different levels of, I guess, diluting the AFFF concentrates. In the NMR experiments that we have, we specifically, because of the lack of sensitivity of that method, we had to actually conduct the experiments where the AFFF was minimally diluted, maybe even only diluted 50-50 in water. So we had to dilute some in order to add the alkali. But in that case, we saw that the concentration doesn't seem to matter, whether or not we started with something in the ppb range or we start with something like almost pure AFFF, which is in the gram per liter levels of fluorine. We saw in the same amount of reaction time, complete loss of all the fluorine features, so mineralization.
Wonderful. Thank you so much. Okay, this is a question from the Racer Trust. Can you achieve low concentrations in your effluent, lower than PPT level discharge standards? How low can you go, Tim?
It's an excellent question. We view this as a concentrate management process. We get the concentrations in our experiments down below detectable levels. I think in the experiments we did conduct, that may not have been to sort of the PPT level simply because we were diluting our resulting samples because of the alkali present in them, because we wanted to protect our mass specs. But we have no reason to believe the degradation follows first order kinetics, and we have no reason to believe that they will stall out at any particular level. So we anticipate that, but I think we probably need to do stronger confirmation of that.
Great, thank you. Okay, this is a question from the New Hampshire Army National Guard. It has to do with the cost, if they are available, for destroying water AFFF solutions, cost per gallon. Are these types of costs available, or are you waiting until you demonstrate your technology at the full scale?
Yeah, it's an excellent question, but I don't think we can answer it based upon the small scale bench experiments we have. All we can do at this point is extrapolate to the energy required, and if we look at the energy requirements we would expect in a full scale treatment system with energy recovery, etc., we expected it would be significantly less energy than incineration. So if we look at what the cost for incinerating the same stockpiles from the input energy requirements, we might anticipate that it would, or what we're hoping to anticipate is that it would be lower than that. But I think it's probably premature to try to offer cost estimates based upon our small scale bench experiments.
Thank you, Tim. And this is a question from the Cape Fear Public Utility Authority. Do you think that your process would work, or have you tested it to treat short chain PFAS such as GenX at low PPT levels?
We haven't tested it with GenX in particular, but the AFFFs that we've investigated do contain a variety of short chain structures in their formulation, things like propane, perfluoropropane sulfonate and their derivatives, and benzoic acid and its derivatives, and we saw destruction of those. You know, I can say confidently there's not a single PFAS we've looked at that hasn't been degraded by this process, but we have not specifically looked at Gen X and those kind of perfluoroalkyl ether structures.
Thank you, Tim. And this is a question from EPA. You talked about the impact of pH. So suppose you're using this technology to treat soil. Would you be able to, what would you do with the soil before disposing of it? Would you, neutralize it given the pH? If you're in the field and you treat soil, would you neutralize it prior to backfilling?
Yeah, I think that's a good question. There would have to be something done to deal with the resulting caustic product. So yes, I believe that that you would do some neutralization. I also think that you would try to remove, if it's a slurry-based system, you'd try to remove some of the caustic and neutralize it. But yes, those are definitely important points that have to be dealt with if you're dealing with the soil. Of course, you're not going to want to put a strong caustic brine based soil back in the case. So yes, I agree with that point.
Great. And one last question before we pull Linda back in and try to answer some of the earlier questions that we've received. Can you talk about the effect of your reagents on the reactor and how many times you're able to reuse your reactor? How tough is this reactor given the conditions that you're operating under?
Yeah, it's a good question. It's one of the things that we want to do in our follow-up work when we have, especially the parts of our work where we're going to be translating from the batch systems to more of a flow-through reactor system, is to look at that stability of the reactor. Certainly that's a question of interest, is what kind of reactor materials are going to be needed to be stable to this corrosive environment. In terms of the batch reactors, of course, we use them for a number of times in our experiments, and we didn't necessarily see any failures like that. But it is a good question, because that is one thing that's going to be necessary, is to deal with the corrosive environment, similar to how incinerators have to deal with a different corrosive environment, which is the hydrofluoric acid. So they're dealing with an acidic corrosiveness. We're dealing with an alkaline corrosive.
And since you brought this up and you're talking about full-scale demonstration, this is a follow-on question from the Vermont Department of Environmental Conservation. When do you think, what is the timeline for making this technology commercially available?
We would hope that we could proceed through in the next few years with, we're currently preparing a proposal for follow-on research that includes this transition to starting to conduct experiments in flow-through modes through a continuous flow reactor, which would be our first step. But also part of that project is working with our commercial partners, including Geosyntec, to develop a plan to go through a demonstration validations and up through the commercialization step. But I would like to say that within 5 years we could possibly be there.
Great, thank you, Tim. All right, we're gonna pull Linda back in, and Linda, we concluded your Q&A with some questions about the next steps for your work. But since you wrapped up, we received a lot of questions from regulatory agencies that are somewhat specific. So maybe let's go through a few really quickly. The first one is from the Department of Ecology in the state of Washington. You showed an increase in sorption with an increase in water saturation. Is that a result of a decrease in available air-water interface? And can we think about this as forcing material to sorb when water saturation increases?
Okay, that's a good question. So those plots that I showed are relative mass, so where the mass tends to reside, which compartments. So that it's true, as water saturation increases, the air-water interface decreases. So that will drive more mass back into the water phase, which will enhance sorption because the concentration in the water will go up. So in effect, it is increasing sorption. So the sorption isotherm doesn't change, but because of that mass moving back into the water, you will get more sorption. I hope that answered your question.
I think that's a perfect response. And here's another question from the state of Connecticut. Does your model include molecular diffusion of PFAS on the air-water interface as a means of transport in the unsaturated zone?
Good question. No, at this time we haven't looked at that. We do have models that could look at that for the volatile compounds, and that would be an interesting thing to look at, but to this time we have not looked at that.
Great, thank you. And then here's a question to both of you from the Angus International Safety Group. And we'll start with Tim. Are the methods that you described transferable to most, if not all, PFAS? Or do the difference in PFAS physical and chemical characteristics impact the effectiveness of the methods that you're describing? Tim?
Sure. So,
and I think you alluded to that somewhat.
Yeah, so
you talked about short chain compounds. But.
Yeah, we believe that it's a general mechanism that would apply to all fluorinated organic molecules. I should say we also looked at trichloroethylene, and we see transformation of that. So we think that there is an attack on carbon-fluorine bonds that would be generalizable to all PFAS. That said, there also appears to be some reactivity differences, and with, for example, the perfluoroalkyl sulfonates being more recalcitrant. So we usually need to have higher, more severe reaction conditions to ensure that they are completely degraded. So there is some structure reactivity trend, which is another thing we want to investigate. But overall, they are still subject to transformation.
Great. Linda, what about your work?
Yeah, so
all aspects of it.
It appears as though a lot of these relationships are compound specific. We're planning, as I said, to start to look at mixtures and also to add in some precursor compounds. And I don't think I can truly answer that question yet. I mean, the structures of these compounds are very different, and so we expect them to have different propensities to move to interfaces and different propensities to sorb. So I don't necessarily think that these mechanisms are going to be important for all PFAS. It's just, that's too much of a generalization. But we do plan to look at others and try to get a better handle on this.
All right, if we try to extrapolate this a bit more broadly, Linda, as you discussed nonlinear sorption, how important is the distinction specifically between linear and nonlinear partitioning for transport predictions in your work? Okay,
so if we just think about one of the compounds, maybe PFOS, at very low concentrations, this distinction might not be that important because all of these curves are somewhat linear. But if you're dealing with a system in source areas where you're dealing with 100 ppb or something like that, then the nonlinearity produces much more tailing and limits retardation more than a linear expression. So if you use the linear partition relationship, you'd actually predict that there would be no limit to the interfacial accumulation, no limit to the sorption, when indeed there are some limits and there is a curvature there. So you actually get very poor predictions. So, but I think, you know, I've been thinking about that question that I had earlier about the, you know, the part per trillion, tens of part per trillion level. I think there the partitioning is still important, but I think the non-linearity becomes a bit less so, because the relationships become linear near those low concentrations. So I hope I answered that. It's complicated.
It is complicated. Can you specifically refer to and direct our audience members to either publications that are in progress and a timeline for that, or when your final report will be available, or to more recently funded work where folks can get additional detailed information about your work, since we cannot answer all the questions that we've received, Linda?
Okay, well, we're working on some additional publications right now. On the modeling side, we're also looking at and trying to look at this mobilization effect that I was talking about for mobilizing NAPLs, and we have some column studies with the Sorption, so we're starting to model those. So we don't have anything right now to share with you, but we're hoping to have something in the next 6 months. That's what I can offer.
Great, thank you so much. And Tim, in general, your work is extremely interesting, but can you summarize how the insights from your project might apply to PFAS treatment in soil and groundwater in a more general way? What have you found to be the most complicating factors and challenges, and what are key things to overcome them based on your work?
It's an excellent question. I mean, I think where we see is, I think one obvious point we see is the scale up question, right? Is everything we've done is at small scale, and there aren't sort of commercial reactors that are at large scale currently available. So I think that's one of our big steps going forward, is just going to be scaling up and demonstrating at scale. Other issues that have been raised that are going to be important is certainly the nature of the caustic product, how you deal with that, and also the stability of the reactor materials. Some of our collaborators at University of Washington have been working, who are going to be working with on these the continuous flow reactors, have been working in these kind of corrosive environments for a while, and have some solutions there they think will work, but we need to test those out. In terms of the PFAS destruction, though, you know, across the board, we think this is something that we think could be very effective for concentrate management. So any steps where you have concentrate streams that you want to manage, we think this has a lot of promise, and so that's where we're focused. Again, I would reiterate that I don't envision this technology as being something that you would apply directly to dilute groundwater that's contaminated. It's still far too energy intensive for that, those conditions.
Great, thank you both for a fantastic webinar and for humoring us with the long number of questions that we've received. At this point, we're going to go ahead and wrap up, but just a few quick reminders before then. Our next webinar is on Thursday, August 20th in the Resource Conservation and Resiliency Program area. This webinar will focus on tools to assess conservation efforts and endangered species on DoD installations, and will feature 2 speakers from Colorado State University and the University of Illinois at Urbana-Champaign. Registration is open, so please visit the CERTUP and ESCCP webinar webpage that Andrea referred to register for this and other future webinars. Before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your participation.